Next we learn about linear span. Definition: let V be a vector space over field F. Vectors u1, u2, un in V are said to form a linear span of V if every V belongs to V. That means every element of V is a linear combination of the vectors u1, u2, un. That is, there exist scalars a1, a2, an in field F such that V is a1, u1, a2, u2 plus an, un. In terms of set, let S be a non-empty subset of V, where V is a vector space over the field F. Then the collection of all linear combinations of elements of S is called the linear span of S. It is denoted by LS. It is clear that S is always a subset of LS, because LS contains the linear combination of elements of S. That means the collection of, it is a collection. So each element is itself written as a linear combination of the elements of S. Yeah. So you know that if X belongs to S, then X can be written as 1 dot X. So X is itself a linear combination of the elements of S, because in terms of other elements, say Y and Z, it can be written like that, plus 0 and so on. So X, each element is itself a linear combination of the elements of S. So S is always a subset of LS. Let us see some important points about span of a vector space. First, suppose u1, u2, un span V then for any vector v in V, the vectors v, u1, u2, un span V. That means if u1, u2, un span V, and if we add one more vector v of the vector space V, then the whole set V, u1, u2, un span V. Second point, suppose u1, u2, un span V and uk, the k is 1 to n, that is uk is one of the u1, u2, un, is a linear combination of sum of the ui's, then the ui's without uk also span V. Third point, suppose u1, u2, un span V, and suppose one of the ui's is a zero vector, then ui's without the zero vector also span V. Next is a definition. Let S be a non-empty subset of V F, non-empty subset of vector space VF, then the smallest subspace of V containing S is called the vector subspace of V generated by S. It is denoted by S within a square bracket. So we have learned about LS. LS is a linear combinations of all the elements that belongs to S, and This set is the smallest subspace containing S. So it is a subspace and it is a collection of all the linear combination of elements of S. So there is one important theorem related to these two, that theorem. Let S be a non-empty subset of vector space VF, then linear span LS of S is vector subspace of V. Also LS is equal to S. So first we have to show that linear span of S is a subspace of V. Let us write down its proof. The zero vector belongs to LS follows from the fact that zero is a linear combination of elements of S. S 0 can be written as 0 dot x for 0 belongs to F and x belongs to S. Next we take any two elements of S. Let U and V are the two vectors that belongs to LS. Then U is a linear combination of elements of S. So U may be written as A1 U1 A2 U2 plus AN UN, and also V written as V as B1 V1 plus B2 V2 plus BM VM, where UIs and VJs belongs to S and AI and BJ belongs to field. For I varies from 1 to N, 1 to N, and J varies from 1 to M. So U is a linear combination of elements of S and V is a linear combination of elements of S. Now for A and B belongs to F, what is the value of AU plus BV? So A operated on A1 U1 A2 U2 plus AN UN plus B B1 V1 B2 V2 plus BM VM. So it is A1 U1 A2 U2 plus AN UN plus B1 V1 BM VM. Now you can see AU plus BV is a linear combination of elements of S, because U1, U2, UN, V1, V2, VM all are the members of S. Since AU plus BV is a linear combination of elements of S, AU plus BV belongs to LS. Hence, is a subspace of V. Next, to prove that LS is the smallest subspace containing S. It is clear that S is a subset of LS. Next, to prove the result, we need to show that linear combination LS, linear span of S is the smallest vector subspace of V containing S. So it is clear that S is contained in LS. Next, we show that LS is the smallest subspace of V. For this, let W be another vector subspace of V containing S. Since S is a subset of W, the linear combinations of elements of S will belongs to W. Because W is a subspace, being a subspace, it is closed under vector addition and scalar multiplication. So the linear combination of elements of S will belongs to W. It means LS is contained in W. It means if there is any subspace of V which contain S is always contain LS. It means every subspace of V containing is always contains LS. Therefore, LS is the smallest subspace S. This proves LS equal to S.